Okay, this is a rather complicated problem, and it's about the crane, and one reason I've drawn it like this with it's similar to what I see in Mastering Physics too. The boom itself is drawn distinctively from the background of the crane and the weight, and that's just to remind and emphasize to students that when you're talking about static equilibrium or anything really to do with forces, even energy, you have to choose your system. What is the object of study? Because this crane will have very many forces within it, and you'll have a most difficult time trying to account for it all simultaneously. So just pick a part and make that your object of focus, and then talk about the forces on that object, because forces will accelerate this object up and down, left and right, and will also twist this object. Static equilibrium is an accounting of forces. Net force in the x direction is 0 if it's not accelerating in that direction. The net forces in the y direction are 0 if it's not accelerating up and down, and you can say that the net, actually let's not talk about, it would be true if we looked about the third dimension, but also for us it's the net torque is equal to 0 if we don't see any twisting. Even if it's not being moved or translated, that's a change in position. If it's not twisting in place, then there's no net torque. So the object of study is the boom. So in order to solve any one of these problems, we need to identify all of the forces on the object. So from the environment, something is creating a force on the object. Forces are pushes and pulls, so we need to look. That only happens at the point of contact. So if I just examine the boom carefully, I can see 2 points of contact. Down here at the pivot point, up here at the top of this boom, and something that's not that obvious in the question, and there could be some kind of confusion, is this is called the guy wire, and this is called the tension in the guy wire, and then there's this tension down towards the load. And actually these two are not necessarily the same, which is not explicitly stated in the text, but it doesn't tell you that this wire is connected to that wire. Indeed, there's actually 2 pulleys on the top, and the way cranes work is this wire goes down into the crane, and that raises and lowers the boom, and then there's a second wire that comes down to the load. Sometimes these are not even in the same location, and then that raises and lowers the load. So it actually makes sense that these two are not connected. So anyway, you can't say, I know the mass here, I know the tension in this wire, therefore I know the tension in the guy wire. No, we need to solve for it. And to solve these equations, we need to identify all of the forces on this object. And the object is the boom. There's clearly a force at this point of contact here caused by the tension. This tension, because these two are because there's this, the tension here is equal to the weight of this mass, because the mass is not accelerating. So I'm going to say right away that I know what the tension is. It's the big mass times g. Actually, I think you're given this value in the text, so in the question, so I'll just leave it. You don't have to calculate for it. Actually, I think they give it as a weight already. In my problem, it's 5,000 newtons. And so I shouldn't have put mass in there because they actually already give you a weight. And then there's going to be a tension here. I'm going to call, so I'll call this tension load. I'm going to call this tension guy wire, or so I'm going to call this tension wire. Tension guy wire. Tension WGW. So the question is, what is this tension? The other forces there's some unknown force here at the pivot point. This is a unknown force. I'm going to call this the force at the pivot. It's unknown. I don't even know its direction. It's going to have a vertical component. So I'm going to call this, I'm just going to call it F. I'm not even going to call it F at the pivot point. I'm just going to call it unknown F. There's a Y component. There's an X component, and these two components are going to be combined to make this unknown. And this is not three different forces. This is one unknown force. I'm just writing it in. It has some Y component, it has some X component, and they'll combine together to make some force. I don't even know what direction they are. When I solve for them, if they're negative or positive, that will give me a sense of direction. And then there's, so I've looked at the 2 points of contact. I've said there's a wire there, there's a wire here, there's some force here at the pivot that's going to push up and out. One of these might be zero, maybe it only pushes up. I don't really know right now, but I'm just making an account. And lastly, there's the weight. It says, it gives a weight for this boom, so the boom itself has a weight, and it's frictionless here, and the distance to the center of its gravity is so many percentage. In my case, it's 38.5%. So what I'm going to say is that the center of mass for this boom, because say it's wider at the bottom, so there's some kind of weight down here, and I'm imagining if this thing had some length, which I don't really know what its length is, but it's going to have one, that if this is the total length, this distance here will be, I'm not sure if this value changes for everybody else, but in my case this would be 0.385, so 38.5% of the length. That's basically 0.385 of the length. That's the length of that lever arm, which from the pivot point. So there's the full length of the boom, and I know that this is acting at a distance that's 38% of that full length. So I put 0.385 of that length. How am I doing for time? Okay, this is getting long already, so I'm going to stop.